All right, so we're in chapter 2 on describing change rates. Now, this is section 2.5 on rates of change defined over intervals. So, when estimating the limit of slopes of secants in 2.4, it was the process rather than a notation that was emphasized. So we had our, x column, x goes to 10 from the left, and then we did x from 10 from the right. Then we had our slope, and we kind of found those, and then we kind of found our limits that way. And this was kind of our notation here, where we did, the f prime of a is equal to the limit as x goes to a of f of x minus f of a over x minus a. And that was kind of all we really did in 2.4. Well, now what we're going to do instead of doing the whole long process like that was we're going to start doing this algebraically. So we can derive the general formula for the derivative at any point x algebraically if we start with beginning with a typical point t. So we'll say it's x comma f of x. And so, they're going to give us some function. So they might give us f of x equals 2x squared plus 3. Okay. So our typical point is going to be x comma 2x squared plus 3. Okay, so that's what this typical point really looks like. Is it's just going to be your x value and then this basically your y value, the 2x squared plus 3. Depending on what you plug into x, depends on what you get for a y. Okay, so that's going to be on the graph of the function. So if we look down here, if this is our function here, the blue line, then we can put our t point here that we just found. It's the x comma f of x or x comma 2x squared plus 3. I don't know, if that's going to work for this function or not, but, it'd be something like that. Then what we're going to do is we're going to choose some point on a graph of f that's a very, very small distance of input away, and we're going to call that an h distance. So from here over to here, that's just a distance of h. And we're going to call that point P, and so that distance or that point is going to be, well, now we just add that h to the x. So we're going to have x plus h, because again, this is going to be our x, and we're choosing, now this, say this is blown up, really, really big, and this is x plus h. Okay, so we're going to plug in x plus h for now x for the p. And then since we have x plus h for x here, we have to plug it in for the x here. So it's going to be f of x plus h. And so now we have those 2 points. Well, now we have a line we can draw through that, and that's called the secant line, and that's that dotted line. Now, the tangent line is really kind of what we're looking for eventually, that the solid gray line. That's what we're looking for. But we're going to be picking these h's that are so close that if we blow this up, this might be, so minuscule that you can't even tell a difference. And when that happens, these two are going to start becoming the same thing. Okay. So then we need to write the slope of the secant line between points P and T. So now we have to write the points and find the slope. Well, how do we do that? We just take the change in y over the change in x. Well, change in y is f of x plus h minus f of x, this point minus this point over the x plus h minus x. Well, guess what? When we do that, that cancels that, and we just have h in the denominator. So now we have the slope of the secant through t and p is f of x plus h minus f of x. And now what we can do is we can find the limit of this, and we're going to have the limit as h goes to 0 because we're going to want to do it with h. And so if we consider the effect of choosing p closer and closer and closer to t, as that p approaches the t point, the length of the interval h is going to approach 0. So we're really, we're trying to get that point, point, t and point p on the graph look like that. But we're going to try to shrink that down until it's basically almost 0 or approaches 0. So we're getting it as close as possible to 0 as we can. And then what we can do is define the interval as the slope of the line tangent to f at a typical point t. And so then it becomes the f prime of x is equal to the limit as h goes to 0, because again, we want that distance from this point to that point, as it's from here to here. We want that h distance to go to 0. So we want it shrunk down as far as possible. And so now that limit h goes to 0 is going to be f of x plus h minus f of x over h. And so we can get our derivative then, or our tangent line, because we're saying now that's going to be tangent when those two are basically on top of each other. It's going to be the tangent. And so that gives us our derivative. So as you can kind of see here, we're trying to get this h value to go to 0. And the only way we can do that is if we pull that p in really, 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 really close. And then what's going to happen is the slope of the secant and the slope of the tangent line basically are the same. And so therefore we can get that derivative of that tangent line, which is going to be our derivative by taking this limit right here. Okay. Now, what do we do with that? Well, we'll see that in some examples, but that's going to be how we're going to get our derivative by taking the limit as h goes to 0 after we've plugged in x plus h into our function here. Okay, so again, so this is the derivative of function. So this is all that's what it's saying when we're trying to get that p as close as possible to t with the h as small or going to 0 as we can. So given that function f, the equation for the derivative f prime with respect to x is f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. And that's all provided that the limit does exist. So we can't do it where a limit doesn't exist. It has to actually exist. And so what we're going to do is we're going to solve this algebraically instead of doing, the two columns for the x going to the, 10 from the left and then finding the slope, and then x going from 10 to the right and then finding the slope. And so instead of doing all that and then finding our overall limit, we're going to plug in x plus h, we're going to plug in x, we're going to have h, and we're going to do all this algebraically, okay? And now the key caveat is it really works best for linear and quadratic functions, because once we start getting higher and higher levels, or, to the half powers or things like that, things get really complicated quickly. So we like to work with these the best. You can do the others, but you really have to pay a lot of attention as you go along to figure those out. All right, so sometimes instead of writing this as, f prime of x, what we can do is we can write it as a derivative, okay? And so it's going to be d dx, and that's how you would say it, d dx, of the negative 4x cubed plus 2x squared minus 5x plus 6. So we're taking the derivative of that whole thing. That's equal to this. And so, before we would say that might have been, if this was an f, as f prime of x is what that would be, okay? So instead of saying the f prime, we're using the derivative notation, and we get the derivative out here. And so this is what we're going to start with. We're going to use this here function up here to help us get to this instead of doing our tables like we've been doing before. Okay, so that's the whole goal, is trying to do all that. And again, all we're doing is we're going to plug in find a typical point, choose some point P on the graph that small distance away, so it's x plus h and f of x plus h. Then we're going to plug it into this formula, and basically we're going to get this. And then we're going to take the limit as h goes to 0 of whatever that ends up being. And then we get done with that, we're going to actually have our tangent line, or our derivative with respect to x, or our f prime, of x. And that's going to end up being this. Okay. So what have we done so far with rates of change? Well, we've done it graphically. We've looked at rate of change of a function at a point. It can be estimated graphically as the slope of the tangent line at that point. So again, that was probably the hardest, because we had to say, well, we'll choose that point and that point. And what are they? Well, we got close. We don't know. Then we did it numerically, which was what we did in 2.4. And so that's how that one works. And we, found the limit of the secant lines passing through the points, and in a series of closer points. So, 9.9, 9.99, and on down until we found what the limit was. And now we're going to do it algebraically. Okay. And we're going to plug in that x plus h in place of x, and work it through that way. And we're going to find our derivative in the algebraic method. All right, so let's stop there and we'll come back with some examples.